Good afternoon. Welcome to course Thermodynamics of Materials. Today we are into lecture 149 and 150. We are continuing with free energy versus composition and activity versus composition diagrams for binary systems AB. This is we are continuing this, and today we consider a different system. That is a second system. System is eutectic system with complete liquid solubility and limited solid solubility. And this is the phase diagram that you see, where the liquid is completely fully miscible. A is fully miscible in B and B is fully miscible in A. So complete liquid solubility, but solid solubility is limited by this composition. Say alpha phase. See, there are limitations of solubility. That's why we don't have single solid solution. That is unlimited solid solubility. We don't have this time. Rather, we have two solid solutions. One is alpha, another is beta. Alpha is A enriched solid solution, and beta is B enriched. That is, it is here alpha. B is soluble in A. B is a solute and A is the solvent. So this is actually A enriched phase alpha, and A can take up in the alpha phase. A can take up to this concentration of B. Hence we speak of limited solubility. Likewise, beta is B enriched phase, and B can take up to this much A. This much A, not more than that. And in fact, this is actually function of this solubility limit is a function of temperature. So this limit decreases as it should be with temperature, and here also decreases with temperature as it should be. So this is the diagram, and this is another thing you should note, that alpha phase has the same, since A is the major component in alpha, A is the solvent and B is the solute. So alpha phase takes the same crystal structure as A. Maybe I will show you, okay, rather I will consider later that that A is the for example FCC phase and B will be an HCP phase, just for example, but later on I will give you. But alpha has the same crystal structure as A, say FCC, and likewise beta has the same crystal structure of B, say HCP, hexagonal closed pack structure. FCC is phase center cubic, and you know that when these crystal structures are different, then the question of limited solubility comes in. If you remember this Hume-Rothery rule, where it says actually there are some limitations about extensive solid solubility. When the binary system, or when this solubility system, this phase diagram doesn't have total solid solubility, under what condition? When number of criteria there, number of conditions are there. One of them is actually, say for example, size difference between A and B. If it is more than, say, 15% or so, then there is difficulty of having a total solubility, complete solubility of A and B. And another factor is electronegativity. That is another. And still another is what? That is actually the crystal structures are different. So one is FCC, another is, say, BCC, or one is HCP, another is FCC, like this. So this is the problem. So that's, in those cases we don't have actually complete solid solubility. We will have limited solid solubility. But in this case we consider liquid is complete liquid solubility, and also you consider it is an ideal solution. Ideal solution means it will follow Raoult's law. So these are the considerations. Another thing I will tell you, that this is you can easily see apparent in the diagram. This is the melting point of A, and this is the melting point of B. and this is actually the alpha phase, and then you and this is the temperature T1. I have drawn a horizontal line because that will be our interest. We will consider temperature T is T1 for construction of the free energy versus composition diagram. This one, and another is one, but that is activity versus composition diagram. This diagram, okay. So this is figure 2a, the phase diagram itself. 2b is the free energy versus composition diagram. 2b, figure 2b is written where? Figure 2b, free energy versus composition diagram. Figure 2c is the activity versus composition diagram. We'll take up one by one and see about the phase diagram. You are all aware of this, but if you are not, then this is the single phase. So go. We have considered temperature T1 because at this temperature T1, if you move from XB is 0 to XB is 1, this across the composition, across the diagram, if you move, you see this actually we come across maximum number of phase possibilities, phase or phase mixture. For example, here T1 up to this point 0 to A we have alpha phase. Then A to B liquid plus alpha phase mixture. Then again B to C single phase liquid, and C to D again phase mixture, what is liquid plus beta, and then D to 1, say 1, I have said the terminal 1 is 1. So D to 1 it is beta phase. It is the beta phase. So this is actually, since we have actually come across the maximum number of phase or phase mixture, so this temperature we have considered, and if we can draw free energy versus composition and activity versus composition diagrams for this temperature T1, we can well expect that we can draw it for another temperature like say T2, say T3, or say T4, etc. We can very easily draw. So this is the most challenging, maybe the challenging temperature why we have actually come across maximum number of phases or phase mixture. So this is the reason why we have considered temperature T1. Only one temperature will be considered in this context, that is eutectic system with complete solids, complete liquid solubility and limited solid solubility. Only one temperature we will consider, and that will be covered today. So this is yes, you have seen this here. It is actually, so it is the alpha phase. Then liquid, this is the phase mixture, liquid plus alpha, as I have already told you. This is the single phase, again liquid. Then from the other side, actually, if you come from the other side, maybe this is the beta phase, single phase, then it is beta plus liquid, then liquid. Or you go this way, again, once more, alpha phase, then liquid plus alpha, then liquid plus beta, then and beta, finally beta. Yes, okay. As I these are the things, okay. And what else? I have named this one, this composition, these points, actually critical points are A, B, C, D. Right here, A, B, C, D, and this side is 0 to A. This 0 is actually XB is 0 concentration, but I will use this for this actually for defining the range, okay. So for nomenclating the name, this zone actually 0 to A to B, B to C, C to D, and D to the other side is 1, U to 1, but actually it is XB, and also XB moves from 0 to 1, and XB is 0 is pure A, XB 1 is pure B. With this introduction, actually we will again I tell you beforehand, before about the free energy versus composition, the two main things, or one main thing, or two main things. So what I said, the cardinal point, key main points, draw the curve for G solution, G liquid solution and G solid solution. Since this we did last time, so G liquid solution, you will see this actually G liquid solution. I have written somewhere G liquid. Have I missed this? G liquid solution should be written somewhere. I should write. I missed this. I'm very sorry that I missed this. It should have not been missed actually. G liquid solution, GL. This I have missed. I should have not. So GL is, since I wrote a much space here. So this I will explain you what is this is GL. Not bad to write here. Okay. GL. Okay. This is the GL. GL, and so this is liquid solution, no problem, only one curve. This I'll explain. And then another is G solid solution, but since there are two solid solutions, so we have to have two curves. One is G alpha curve, the red G alpha curve, and another is G beta curve. So and then compare, okay, their relative positions, or if they are coexistent, or there are presence together, that is coexistence of these two, either single phase domain or phase mixture domain. Okay, so in case of phase mixture, you will have a common tangent. Don't forget what I say, common tangent, phase mixture. And when it is actually no such situation, okay, no such possibility, then you have to see which is upper curve and which is lower curve, or which has higher free energy and which has lower free energy. The lower curve of the smaller free energy will be the stable phase relatively. For then this I often say for a given composition. And when the two curves are non-intersecting, these is actually some tricky points I gave you, that this you will follow. These tips I gave you, that non-intersecting and actually same for the same composition. But in case of two coexistence of two phases, there are two compositions. One has the liquid, another is the solid. They are coexisting. So they have a. So this you will see here also. You have a common tangent. So two phase means this actually there is a common tangent. So this is the free energy composition diagram. I will elaborately discuss. And then the last you will come this figure 2C, activity versus composition. Again see same thing. Activity of B liquid will be plotted on the y-axis, and activity of B solid, rather, I'm very sorry, it is better I say activity of B L means what? Activity of B with respect to pure liquid B as standard state, like last day, exactly like last day. And activity of on the parallel y-axis, activity of B S means activity of B with respect to pure solid B as standard state. This parallelly will actually present, and accordingly, if you follow this curve, say the lower curve, you see this arrow, yes, this activity of this curve, AB liquid means this one. This shows the arrow is pointing towards this axis. So this curve, lower one for this scale and upper one for this scale, AB solid also written. So it is actually repeatedly written AB solid and AB solid. This arrow shows this y-axis, and the x-axis is unique for both of them, common, that is the composition. Activity versus composition moves from 0 to 1 like this, 0 to 1, 0 to 1 phase diagram. Coming from phase diagram from the free energy versus composition and activity versus composition into this is the same. And these are projection points, these critical points are projected, and you have this, okay. So these are the things. And remember two things, this ABL and ABS, that is a standard relation. Remember this ABL is E exponential of minus delta G0 melting of B by RT. So and times activity of B S. Okay, these two are related by this. So this will be found here also. Same thing. Again, this horizontal line means two phase mixture. Two phase AB, see AB, two phase mixture. So you can anticipate these situations, okay, beforehand, okay. And you see, and you have actual ideal solution behavior you expect for the, since here it is already I have told you that liquid solution is ideal. Complete miscibility, liquid miscibility, or not only that, it is actually not non-ideal. It is an ideal solution as well. It could be non-ideal, but ideal means it is even simpler. Simpler means it will follow Raoult's law. Activity B is mole fraction. So if you have drawn a line, it's a dotted line. Actually, I drew first. AB is XB line. I should have written this, but I didn't write this. AB is XB line. Shall I write anywhere? This is actually the dotted line. It will be too clumsy, but I tell you what, 0 to 1, you connect 0 to 1, so it is actually AB is XB line. AB is XB line, AB is BC, AB is XB line. Okay, anyway, So last time I actually showed this in the last discussion. So AB is XP line. So what we expect, that since liquid solution is ideal, means B to C domain for activity of liquid. AB with respect to pure liquid B as the standard state. So liquid B is the reference state and the solution is also liquid. So you can expect, if it is an ideal solution, AB is XP. So it falls on AB is XP, on this AB is XP line. Okay. Here, shall I enter? Okay. I may write maybe here somewhere. I write somewhere actually. I'm doing this. I'm showing you this one. I'm using this space, this one, this car, this. There is a dotted part also, dotted. Actually, initially it was dotted only in this segment when the actual curve falls on that line. It is actually, this is a solid line, but this is a dotted. AB, what is the name? AB is XP line. This is AB is XP line. Okay. So as I told you, so since liquid solution is stable in the BC segment, so in BC segment you have this AB liquid is given by this AB is XP line here. You don't expect this for the solid because AB is XP, AB solid, but you are considering actually for the liquid phase. For the liquid phase, this is a straight line, but this is actually straight line, but this is not AB is XP, because AB solid is the considering solid B as a standard state, but the phase under study is liquid. So in the domain of BC, you don't expect AB solid will follow AB solid is XP. But in the same domain BC, AB liquid will be XP, because liquid, this is the solution is liquid and reference state is liquid, pure liquid B as a standard. But anyway, this will actually I will discuss later. So just I tell you briefly what is going to come, so that you actually have no difficulty. So I have shown here this AB is XP line, this one whole, okay. This goes, I tell you what is AB is XP line. Start from here 0 to 1. Connect this, and you see anytime you actually want to draw this later on, I tell you, you just check. You first draw which part. I would say, if you ask me which part you would draw, the liquid which is easier, which is easiest. No, that you consider, oh, this is pure liquid and it is ideal. So activity of B with respect to pure liquid as the standard state will be XB in this domain BC, as you see. So you do what? You will just draw that line, superimpose on the dotted line. If you have dotted line here, dotted, this segment BC, you just complete this. So this part is over. Then you have a two-phase mixture. So then horizontal, and this side is also two-phase mixture, horizontal. Let's see here also two-phase mixture. Then how you terminate this? Then that is different. So I'll discuss at length. Okay, and so unnecessary. Okay, I will not. Okay. Jump upon this thing, okay? So go sequentially, start. So this is the Eutectic system with complete liquid solubility and limited solid solubility. So let us have some, okay, here. So the phase diagram let me give you the phase diagram. What I said, actually I will elaborate here in the subsequent discussion. The phase diagram for the eutectic system, system is given in figure, is given in figure 2a. 2 actually, this is the second item, second topic, okay, under this free energy versus composition and activity versus composition. So second system, so 2 and figure 2. Okay. 1 is over. So 2, and there will be another, there will be a third after this, okay, may not be today, next class. So today we will complete this. In figure 2a, the liquid solution is given is considered to be an ideal solution. Ideal solution the solid solution shows positive deviation from ideality. Oh, that's another point that I missed. It is not ideal, but positive. When you have a positive deviation, then there is a phase separation, like alpha, beta. The consequence of positive deviation is this: there will be phase separation. So, and negative deviation, the consequence is it is tendency towards a compound formation. In the intermediate composition, there will be compound formation. Tendency of this, or the intermediate phase, sometimes we say, with very small composition range. And when it actually say have a strict rigid composition, then we say it is a compound, stoichiometric compound. And this happens when the two components show negative deviation from ideality in the solid state. But liquid is over. Liquid actually we have considered it is positive deviation. I am very sorry that it is an ideal solution. Okay, so follow ideal solution means it is Raoult's law and activity is mole fraction. Remember activity. Okay, with respect to the standard state, the same physical state as the state under study. Remember, then only you apply activity is mole fraction. Otherwise you don't. So as you will see here, okay, and you have already seen a number of times. I have focused this, okay, this point. I have pinpointed this point. The solid solution shows positive. So positive deviation. Positive deviation is what? Activity is greater than mole fraction. Then there is the activity coefficient. And then gamma is coefficient greater than 1, which means activity will be greater than mole fraction. And so ideal solution is, remember, activity is mole fraction, and negative deviation was activity less than mole fraction. So positive deviation, the solid solution shows positive deviation from ideality, resulting in phase separation. This is alpha and beta, as I have already said. The terminal solid solutions that is namely alpha, this end and the other end A and end B, terminal. solid solutions are alpha. That is what we say is this is A is the major, B is the minor. Alpha. A is the major, B is the minor. A is the solvent, B is the solute. Okay. So solubility of B in A. B is solute is dissolved in the solvent A. So solubility is what it is, solid solution of B in A. This solid solution of B in A, where A is the hence A is the solvent and B solute. Obviously the solute. Okay, this is this, and beta, the opposite. Beta is, you can write solid solution of A in B, just opposite. Here B obviously will be the solvent. The major component is solvent and A the solute. This is about the alpha and beta introduction. Okay, solute. As before, as I tell you, as before, our main concern will be the drawing of the drawing or construction may be better word. It will be the construction of what? Tell me. Construction of G liquid and G solid. G liquid and G solid. Curves. Okay. G liquid will be drawn. No difficulty about G liquid, like last time. No difficulty. The same principle. Solid difficulty, because there are two solid solutions, alpha and beta. So let us see what we do. What can be done here? Okay. So G liquid. What is this? G liquid will be GL for short. Liquid will be drawn by graphically adding what? Graphically adding the delta Gn ideal curve. Why we consider ideal? Actually, it should be only delta Gn. In principle, delta Gn. But ideal because we have considered liquid solution is ideal. If it is non-ideal, no problem, the non-ideal. But mixing, delta G free energy, integral free energy of mixing. Okay. Remember always that we have plotted here integral molar free energy is plotted against Xp is the composition. This is temperature against composition, and this is activity of B against composition. So delta Gm ideal curve, adding this with the adding to the what? G unmixed liquid curve. This we know. Just add this to curve, graphically add. Mathematically, you know, of course, 100%. But since graphically we are actually presenting, so okay, curve. See, each graphical curve has a mathematical counterpart, mathematical representation. So add this also, no problem. So for example, what is the delta GM curve is actually, I tell you what is this mathematically, RT XA ln XA, RT XA ln XA plus XB ln XB, RT times whole times RT whole times XA ln XA plus XB ln XB. If it is non-ideal, then what it will be? Delta GM is, that is more general, more powerful, more general. RT XA ln A activity rather than mole fraction. Activity A plus XB ln AB. Okay, careful about this point. Okay. So this is these two curves. You have to add this. So the equation corresponding to this, and for what is the unmixed, it is written here. XA GA0 liquid plus XB GB0 liquid. So mathematically always you have the backup. So no problem, no problem. One thing very important, I am very sorry. Warning, okay? Warning, or what should I say, okay? Okay. Warning. One thing about last day's mistake. I'll remove this part, okay? This line. But here last day's error. Grievous error. Grievous error. What I say, what I wrote? I wrote what? Delta G unmixed liquid or solid. So coming to solid, I wrote. So read delta G unmixed is as G unmixed. It cannot be delta G. What is the delta G? What is the difference? G of unmixed liquid. What is that? XaGA0 liquid plus XbGB0 liquid. Okay. So read this as this. This is correct. This is correct. This is incorrect. Why this delta? Incorrect. This is correct. Similarly, okay, notice what is this right here? G unmixed liquid is what? What is this? Delta G, I wrote last day, delta G unmixed liquid, that which is erroneous, is what? Is XaGA0 liquid plus XbGB0 liquid. This part. Okay, so this is strike of this. Okay, so so this is only G. This today actually I have written correctly G unmixed liquid. Similarly, the last day's class. Similarly, what is read delta G unmixed solid as what? G unmixed solid. Read delta this. So right. So you don't see them. This is incorrect. This is correct. Okay. Since I am using again, so today I have not made any mistake. So G unmixed liquid curve. So this you will note this part. Note this part that you should not be careful. Please correct this. I am very sorry that I actually okay, on the spur of the moment I wrote that, but I should have been more careful about this, that it is not delta. Only what you have. So sorry. So this part is over. Okay. So this that is carbon. What is this? What does it mean? What is that? G liquid solution. I can write this. G liquid solution. Liquid solution is nothing but that is GL in short. GL is delta GM. Delta GM in general, delta GM. Delta GM, delta GM in general, delta GM plus, what is this? X-ray GA0 liquid, unmixed one is what? Unmixed means they are pure. They are pure. So GA0, standard state. When they are mixed, they are impure and become solution. So pure plus X, and X-ray is because their contribution. Mole fraction is their share. Their share. That is the weight. Weighted, okay? Value XB, GB0, liquid. I think you don't have any difficulty, okay? The DL is delta GM plus this is delta. This is the change between this and this. Because in case you want to know more, that is I should write G2 as if this I showed you when I was introducing delta GM while studying solution thermodynamics. This is the G2 final state, the liquid solution, unmixed state, initial state. This is initial state, and their difference is when this starting with this state we get this. What is this? This is the difference between G2 minus G1. This is nothing but delta G system. Delta G mixing the process as process. Considering the process, it is mixing process, but it is delta G system. We are used to considering the system surrounding, etc. System particularly, delta G system. And the second law is delta G system is negative for spontaneity. Delta G system is what? Delta G system is what? It is actually, delta G system is, this is nothing but is G2 minus G1. So just to revise what we had read before, but nothing else. So this is fine, very good. So, and if you ask me, sir, coming to G solid solution, next I will show you first. I have an obligation to show you that how you have added graphically. You know, like last time, follow slowly. What is your delta GM curve? This is this curve. I have written somewhere here delta GM idea, and this is very standard. So this curve, okay. Actually, which undergoes a minima at XB is 0.5 exactly. Mathematically, it can be shown. So delta GM ideal curve, this one. I have written here. I have shown here. Delta GM ideal. This one. I show this. This. Delta GM ideal. Add with this this one. G unmixed liquid. What is that? This curve. This straight line. This straight line. This is GA0 liquid. Achha, by the way, I have a lot of things to say. How will you get X-ray GA0 liquid, HBG liquid? I am not, yes, actually. I am sorry, at the beginning I should have said that. Remember, you have to put a reference value. Because you know, you already absolute value very difficult to know. I am talking of G alpha, or G liquid absolute value. How should we get this absolute value? Free energy absolutely is not known. We deal with changes, first law, second law, everywhere. So absolute. But since we are dealing with this, we have to find out GL and G solid, etc. So we have to start with a G value, absolute value for a solid or a liquid. This side, and B solid or B liquid. Which I will consider? See the temperature T1. It is below the melting point of A. and likewise this same temperature T1 is below the melting point of B, means solid A and solid B is the stable state, so that they have lower free energy than their corresponding liquid state. So solid A has the lower free energy than liquid A, and solid B has lower free energy than liquid B. So the lower one you consider 0. So A solid 0, A solid. I have written FCC. Structure is another important issue. Here structure is you have to write. It's better you write this, because this FCC structure, that is why you have this phase separation. So additionally I have mentioned what type of solid, FCC crystal structure. What value I have assigned here? 0, Ga0 solid, because in any case FCC or whatever crystal structure, it has a lower free energy than their corresponding liquid, means A liquid. So this is 0. If it is 0, then Ga0 liquid will be above this, somewhere above this, governed by, as I told you, delta G0. In fact, delta G0 melting, but more simply, more easily, by enthalpy of melting and melting point. This I gave you expression. So giving this, you can fix this point. Suppose this is the point, Ga0 liquid. So this point are final. Go to the other side. Again, B solid since below the melting point. So this has a lower free energy than the liquid B. So consider 0 value for B solid, it's GB solid. I have written here GB0 solid because it is standard state. Remember, I have written here B solid, but at the bracket HCP crystal structure. This will be required. Okay. So HCP, this is a structure, but solid has 0 free energy assigned. And if it is assigned, then the liquid will be a perfect, exact value, because governed by that delta G0 melting value. Okay, and also that in turn on the enthalpy of melting and melting point, etc. This part is correct. So exactly once we have assigned, we have to assign. Then the other part, this is the, when I place this is 0. This is the point. This is the point is what? B liquid. So B solid, B liquid. And value is GB0 liquid free energy. And plotting integral molar free energy means actually 1 mole free energy. Integral is when you are combining A and B, then integral molar free energy. That is for G alpha. I am very sorry. First of all, that is for G liquid and G solid. Integral A and B together. So that's the integral molar free energy. I have already discussed integral molar free energy. And integral total free energy, okay, all these things, okay, very good. And partial, so molar free energy. So what is, again repeat, 4 points: A solid, A liquid; B solid, B liquid; B solid here, B liquid here. These are zeros, assigned 0, A solid, B solid each, because both of them have melting points above temperature T1. So T1 temperature, they are below melting point, so their solid phases are stable. And in which form? One is FCC, another HCP. This is the reason why there is actually not complete extensive solid solubility or thorough solid solubility, complete solid solubility, total solid solubility, no, limited. That's why 2 phase separation occurs, and alpha and beta. So this is very important crystal structure. So I mentioned also. So if you look carefully, you will see this. You will see them, that it is written there. It is discern these two, okay, words, okay, FCC and HCP, okay, this abbreviation. So now given this, then what is this line? This is A liquid, and means having Ga0 liquid value. Ga0 liquid is the free energy here, and it is Gb0 liquid, and this is B liquid. This point is B liquid having a free energy of Gb0 liquid. Connect this will represent XAGA0 liquid plus XBGB0 liquid. So this term is this curve. Add this curve graphically and this curve. What will result? This curve. This, okay, this, okay, this is the curve. This one, this is curve. And what I have named this? Obviously GL. See GL, you can see. This one, GL. This part is easier and over. Next, obviously G alpha and G beta. I've already shown this by red curves, but this may be little bit difficult, involved. This I will explain. Okay. So this next, let us keep on about this now. Solid solutions. Now this time two solid solutions. So one by one. So let us write this. The curves for G solid solution. G solid solution is in the present case, split into two, what are they, namely G alpha and G beta. Note this splitting, this split is due to the two different crystal structure, due to the two different crystal structure, two different crystal structures of A and B. Of A and B. A is A, we have considered FCC. Just we have considered FCC solid. A FCC, B is HCP. B is HCP, hexagonal closed packed. FCC is face center cubic. Okay, so this is abbreviations. The constructions of full stop. The constructions of G beta and G alpha curves construction of the curves is in accordance with the following steps or considerations. Steps or considerations or principles. Questions. These I will actually mention. Note both A, which is FCC solid, and B, HCP solid, are assigned a zero free energy. As I have already told you, zero free energy. Zero free energy because they are because they are equilibriums. They are the equilibrium states or stable states at T is T1, which is less than T1 which is less than both TMA melting melting point of A and melting point of B. T1 is below melting point of A as well as melting point of B. Okay. See if suppose if it were not, suppose it is below A, I have shown you previously. Then so suppose it is below melting point of A, then a solid as here would be assigned a zero value. But it is suppose it is above the melting point of B. Suppose the melting point would be somewhere below for B, then liquid is the stable phase. Liquid has lower energy, so it will be not B solid will be assigned 0, B liquid will be 0. This I discussed last class. Okay. So detailed. Okay, you see this changes occur. So depending upon T1 temperature and T2 temperature, there are difference. So you can check back there. So but anyway, just in passing, you note this point. Okay, so. Also, note that the alpha phase which is a enriched phase. The enriched phase is of FCC crystal structure. This is easy. A has the crystal structure of FCC. Alpha phase where there A is the solvent matrix, and B is actually suppose substituting certain points, certain sites, replacing A. So crystal structure remains the same. Matrix. What is that? In this is the same structure as the A, which I consider FCC. So alpha has the same crystal structure as A. Likewise, beta will have the same crystal structure as B, because B is the dominant in case of beta, and in case of alpha, A is the dominant. So A's crystal structure is retained in alpha, and B's crystal structure is retained in beta. So careful about this structure. Also note that crystal structure and the beta under the alpha, and the alpha is which is A enriched is of FCC crystal structure, and similarly, right, and the beta which is B enriched phase is of what? B is the HCP structure, so of HCP crystal structure. The first point is over. So about the other points, let us move to the top. This is now important. The second point and third point, that is the construction of G alpha and G beta. How I question. Second point will address how I constructed the G alpha curve. This is the G alpha curve. I have shown here, but it has again. This is actually further division, further explanation of construction of alpha. Because you know that G alpha should be drawn what? G solid solution can be drawn which principle? With the delta Gm curve for the solid alpha, for the solid solution say in general, plus unmixed G unmixed solid. This is the principle. This same principle is adapted here, and the outcome is this curve G alpha. So I will show the component two curves here separately and add them graphically again and show that how this curve was generated. Similarly, how this curve G beta was generated in the second point, one, third point, the other. This is the next job. Okay, the construction. This is actually, see, G alpha. I have said G alpha, but with construction here is not shown. See, in this diagram there is no how I got G alpha. Should be from delta Gm solid solution plus unmixed solid. Where are they? Where are they? I have just given the final one, the result, but now I will show the component values and the addition. So take up. Let us write this first, then I will show you the G alpha curve. Now about the solids, there are two divisions. One is alpha, another is beta. G alpha, G beta. Okay, so G alpha curve, one by one. This section is G alpha curve. Is about G alpha curve. G alpha curve can be drawn by adding delta Gm alpha. Alpha is this delta Gm I am writing. Okay, it is better I don't ask this, but I write this. Non-ideal. Delta Gm ideal for liquid. For liquid behaves ideally. Behaves ideally. This is considered. Complete solubility and ideal also. But delta G is sure it is non-ideal. Because already we have seen what we have considered or what we have inferred. It is a positive deviation from ideality, means non-ideal. So delta Gm alpha is a non-ideal. This delta. So anyway, this figure you don't get. I'll show separately. The final one you have got G alpha. So careful. Delta Gm alpha is a non adding this curve delta Gm ideal non-alpha curve. I should write this side curve to the G unmixed solid, unmixed A and B, unmixed A and G unmixed A and B I think G unmixed to the G unmixed A and B. Okay, let it be so. Let us see. G unmixed A and B, both of which both of FCC structure. Both of FCC structure. both of them with FCC structure. Both means A and B. So why this is actually, let us write this out. Both of them have since what is the reason both of them with the FCC structure? Since what is why? Because since alpha has the FCC structure, since the solution that we get alpha is an FCC structure, since alpha has the FCC structure. FCC structure. Since alpha has the FCC structure, so we have to add what? Unmixed A and B of what? GA FCC and B also FCC. Then only it will actually justify this alpha, G alpha. But where shall I get FCC? Where shall I get BFCC? B is HCP. B occurs in HCP structure. BFCC, we don't get any data. So B says, what about B solid here? B liquid I have placed here. Liquid is above certain temperature, it will be liquid. But normally we don't have this structure. See, BFCC is not possible. A likewise, AHCP not possible. This impossible thing we have to consider theoretically. How to handle this? So this is possible, then impossible is given by what? Now delta G is positive for the change. B, since I am talking about A side, A FCC to A HCP, this delta G, very high, delta G is positive, large positive, very large positive, extraordinarily large positive. So it is impossible. That's why it is impossible. That's why you will never get A as HCP. A as HCP. But, so you have actually, so I'm sorry, actually, where A is already FCC, since we are talking about alpha has the FCC structure, so thank you. So, so I'm very sorry. So B actually, the problem is actually, sole point is B. A is FCC, alpha is FCC, so B must be FCC, but B is HCP. Free energy of B HCP is as significance. We have considered that 0 value. Liquid is also, liquid is not stable at this temperature, solid is stable, B is solid, but has free energy. Similarly, B FCC, B solid FCC must have very large free energy. That's why it is not possible to have at any temperature much higher or much lower. Only one allotrope of B, namely HCP. One form of B, crystal structure, HCP. But in principle, you can say, yes, since it is impossible, means our thermodynamic interpretation is that you have a large free energy. So that we use. So we have to pinpoint a free energy value, assign a value, have a value. We will say that it is very large, but you have to confine it within the diagram. So try to make it as large as possible in the diagram. Then you will get BFCC, which is BFCC. Then connect AFCC and BFCC, unmixed. And then delta GM ideal, I already have said, I'm sorry, delta GM alpha, which is non-ideal. That has equation also. RT, XL and A plus XBL AB, that you do this. This I will show you here, this side. This is not possible to show there. Follow me. Okay, alpha has FCC structure. Since alpha has FCC structure, okay. The question is now. The question is now. What is the GB0 FCC? GB0 HCP is here. GB0 FCC. Huh? Way above it. 300 critical. That is the answer. What is the GB0 FCC? So, question is, what is the GB0 FCC? Because the EP, because answer I am giving, because the BHCP, see I am talking about BFCC, BHCP. Similarly, this side when I am come AFCC and impossible AHCP. Possible AFCC, this end. Give and free energy to this impossible phase. Impossible means we have no idea. We don't see that phase in books or anywhere. But liquid is possible. Liquid at this temperature, solid is pure, but liquid has free energy. Liquid we have put here. Liquid. This is not same comparison. Liquid at above certain temperature, for above this temperature, liquid is stable. Is there any temperature we know that where BHCP will appear as BFCC? This is a cadmium, magnesium, HCP structure. Zinc FCC. We don't know. If we know, then that we have to put there. If we know, okay, if there is actually sometimes actually some different temperature. Iron itself has a different crystal structure. FCC at certain temperature range. Up to 910, it is actually BCC, from room temperature to 910, and 910 to say 14. Okay, this is actually this temperature is around that 1490. This is actually the range of FCC. And then beyond this, actually there is delta phase. Okay. This is actually so delta is again BCC. That is again BCC. This temperature. So I have multiple structures. This is possible in the depending upon the temperature. But if it is not, so in principle we say, well, since we don't have a higher pH, and since we actually don't know of this higher, very high pH, so because the BHCP is the stable form of B solid, the occurrence of BFCC is impossible. That were possible, BFCC at a different temperature, like iron. Above 910 it is gamma iron, FCC iron. Below BCC. If it were possible, then we will see this in the diagram. In iron carbon diagram, iron you see different form. But here, where do you see? You don't see. But you have to draw a G alpha where alpha has the crystal structure of FCC. So you have to hypothetical case. What would be the free energy of B if it were HCP? As in this question, I'm very sorry. If it were FCC, if it were FCC, it is actually HCP. If it were FCC, what would be its value? This case, okay. And similarly, this side, A is FCC. What would be the free energy of A? What would be if it were HCP? It is not. Do we see in the phase diagram? We don't see. Okay. Very good, very good. Okay, so this is actually. So the occurrence of BFCC is impossible, and hence BFCC will have much higher. In principle, when it is not stable, it has a higher free energy, say, than compared to the stable one. But since this is actually hypothetical, it is not. It is a theoretical question. Much higher. Much higher, you can write extraordinarily higher, exorbitantly higher, inordinately higher, much higher. So higher would be good enough. But since this is liquid, for liquid we write higher. But this is nowhere to be seen. So much higher. When a phase doesn't exist, you will say it has a very high free energy. That's why it doesn't exist. This is the answer. Suppose sulfur has actually, sulfur H2 gas has many forms, different forms. H2 gas, sulfur gas, diatomic, triatomic, H2, H4, H6, H8, gas, all gas. But if you ask me what is H7, H7 doesn't exist. You don't see this. Then what would be your answer? It has very high free energy compared to any of them. That's why it doesn't exist. Why it doesn't exist? Because high free energy. So high that it doesn't exist for at any temperature. And if it were in any reasonable temperature, then it would be available in the data book. That's why so many are already. Not only H2 gas, H4, H6, H8, much higher. Then we will have much higher free energy than BHCP. That is, what is the free energy of BHCP? We have assigned 0 value. Okay, much greater than 0. 0. This is shown in figure A. Figure A. I have given this A and the next one B. Figure B. This separate. I will draw you. I will draw you here. Below maybe, then I will write actually figure A, figure B. Here, figure A I am drawing you quickly. It is better I write, draw here. Sorry, right here. Figure A. Let us see. It is not difficult. Sorry. figure A. I'm drawing freehand, okay? So, so it's just, okay, you consider 0, 0. 0, 0. First you do this. This reference is very good. 0, 0. Who is this gentleman? This side, tell me. A FCC. FCC. The stable. This is what for BHCP. BHCP. Okay. A FCC. This is a okay. This. What would be the B? The question is about BFCC. BFCC will be higher. Where it will be? Higher means will be here, 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 here. Goes to infinity. As if very, very large. So it is impossible to exist, to form, to observe. So I cannot, I have to contain this in this diagram. So I am showing you here, you understand this. This point is nothing but, you write here B, what? BFCC. BFCC. So you have AFCC, BFCC. Unmixed one plus delta G. So let me draw this unmixed one. Oh, sorry. Better I come down from this side. No, I don't know. Not bad. So this is the unmixed, right? What is the curve? This curve is what? Right? Right here. Right here. XA, GA0. FCC, this time FCC plus XB, GB0, FCC. Unmixed, right? Unmixed part. Unmixed curve. G unmixed. What then next? Delta GM. Delta GM is cannot be like ideal. See, positive deviation. So what is the curve? Curve will be little bit, will rise little bit from this one. And with negative deviation will descend little bit, will fall little bit. So rise little bit, so not bad. Let me draw for delta. This is for what? Delta GM alpha. Solid solution I am drawing. Solid solution. Alpha. It is all about alpha. About this curve, this red curve. How it is constructed. Delta G alpha I have written correctly. Alpha. What I should write in addition? Where I wrote delta G ideal. Idea. Delta G alpha non-ideal. I have to write GM alpha non-ideal. That is very important. You know, this is a positive deviation system in the solid state, non-ideal. And what is the equation? If you ask me, that I can give you very easily. RT, XA, tell me, X times XA ln general one, XA ln A, activity A, not XA. That is for ideal solution. When A is XA, A plus XB ln AB. That's it. AB is greater than XB, A is greater than XA for positive deviation. Okay. This is the drawing right here. Okay, this is this. Okay, XB. This is actually A. This is right here. XB here. You can give this 0 to 1, and again you write. Don't forget to write this integral molar free energy always. These are integral molar. This is integral molar free energy. delta Gm alpha for mixing. Integral molar free energy of mixing, n for mixing. Integral molar free energy. Like this. Free energy. Now these two add this. Now the conclusion or climax. This delta Gm plus unmixed. Delta Gm plus unmixed. This is written here. Gives you G alpha. So if you do this, maybe I can show you how it will be. This and this, if you had this, this actually, this is what you write. This is G, your desire. G solid, one of the two solids, G alpha. This is shown where it is G alpha. This part is over. Shall I repeat anything here? 0, 0, as it should be, because stable structure is FCC for A, HCP. For B, as a jar assigned 0. But question is we have to get B FCC. FCC, free energy of B in the FCC form. Very highly positive, high positive value. Impossibly high perhaps. Okay. But suppose we have to show here in the diagram. So consider this, we have this. Then both are FCC, and the solution that will form, namely alpha, will be is also FCC. This is known to us. You get same structure as the A. So you first then combine. This is actually XAGA0 FCC, no solid. XAGA0 solid, FCC means crystal. Solid plus XBGB0 FCC unmixed. This is the underline. This is the unmixed part, and this is the delta Gm. Not as a non-ideal, alpha is a non-ideal solution, and this one. The curve is this. This will not be like this. It will slightly above it. Absolutely. Delta G ideal. So these two curves graphically added, mathematically added, is what you generate this curve, which is there. So this part is over. Similarly, G beta curve. It is paraphrase this. Just paraphrase this. So third, and this I will show you. The G beta, similarly, the G beta curve just can be drawn exactly, can be drawn by adding. Tell me here what will say delta G mixing of beta, non-ideal. Both are non-ideal. This side is non-ideal, that side is non-ideal. Non-ideal. Just write this here. Non-ideal curve to the G unmixed. G unmixed to the G unmixed of unmixed B and A. I am writing B first because it is B enriched. The side of B enriched, B dominant, B and A. B is the major, B is the solvent this side. Beta has the same crystal structure as B, beta. A has taken shelter in B, this side. A solute taken shelter, occupying some lattice positions, some of them, maybe 10%. Remaining 90% beta original, B original. So retain the crystal structure. So G unmixed B and A, like here G unmixed A and B, both of them here you write in bracket maybe G unmixed B and A, both of B and right. B and A, okay, G unmixed B and A, both of them them means what? Them is what? B and A, both of them, B and A, who are them? Don't mix up with these other things. Them means here B and A, and here them means A and B. If you want to add here, them means A and B. This is the them, A and B, with what structure? HCP structure. Is a B is original HCP, and A must be also HCP, which is difficult, which will be challenging. So with HCP structure, both of them, A and B and A, with HCP structure. Since, write in brackets, since, why HCP? Why we insist on HCP? Because the beta base is HCP. So add with B A of HCP nature, so that you can go to the other side. Continuous, it will continuous one. HCP and HCP. And for this purpose, you have to consider some theoretical consideration. Since beta has the HCP structure, so that's why we are focusing on HCP. Let us have the free energy of either A and B, A or B, or say both A and B, same structure, namely HCP. In this case, for beta, free energy of beta, G beta consideration. But since B has the HCP structure, since the, again you can write it the same way. The question is now, okay. Let us shorten this. The question is now I am not writing, but this is the same way, right? Because the AFCC, just I am writing and dropping one sentence or this, okay? Because but main thing I am writing, because the AFCC is the stable form of, is the stable form of a solid, the occurrence of a HCP is impossible. Like this is impossible, and hence a HCP will have much means much higher free energy. Oh, I'm sorry. This is shown in figure A. So please let me write here. This is very important. Figure A. Please note this. Figure A. Already over. Figure A. Now next will be figure B actually. For G beta, figure B. So we'll have much higher free energy. We'll have much higher free energy than A. Then it is better I write this side. FCC, that is much greater than 0. This is shown in figure B. This is shown in figure B. I may draw here. I may draw this here. Okay. So figure B. Similarly, you start. You draw this here, like this. Start. Oh. Shall I? That's okay. That's good enough. So what you do? Here, right? The middle somewhere, here and here. Draw a line. This will be 0, 0, 0, 0 line.
1 hour 31 minutes gone.
Okay. 0, 0 line. Okay, thank you. This
How
is,
much
left?
left?
31 or 2 hours.
2 hours.
For 50 minutes, you just check. 50. When it is 1 hour 50 minutes. Okay. What you should write here like this. This is what this side is normal now. Is regular. Regular is beta. You write here beta. HCP. Beta HCP. Okay. Beta HCP is right. And this side is 0 is A FCC. Again write integral molar free energy. Integral molar free energy. This is XB 0 to 1. This is A. This is B. Beta. Okay. This is 1. This is okay. This is 1 0 line. Now where A HCP will be? We need AHCP. AHCP will be where? You know? Will be above this, much above this. So say this point. So right, this is free energy of AHCP. This point. AHCP, which is impossible. You may call it absurd. But thermodynamics says it is because delta free energy of that phase, that species, that component is very large. That's why it doesn't exist. So, but I cannot show actually at any higher values because I don't space limitation. So I consider this is that. Then what you will do? Obviously unmixed. First is unmixed. This is the unmixed. Okay, right? What is this? You tell me what is this? Like this. Xa Ga0 HCP, or both are HCP. This is HCP. Okay. Sorry, these lines are actually. This is B. B HCP. B HCP. Xa Ga both. This is HCP. That is HCP. Okay. So Xa and Xa Ga plus XB GB0 HCP. What you write here in addition? Unmixed. This is actually unmixed. Unmixed free energy. G unmixed. Okay. It is better to write here G unmixed. G unmixed. G unmixed, right? So it is better write G unmixed. And then add delta Gn. Similarly here, positive deviation, slightly above this. So say this. So right here, what is this? Right, delta Gm. Of course, delta Gn for what? This is a solid solution. Remember, this was a liquid solution, though. But equation delta Gn, what you write here? Beta. Beta is another solid. This solid solution. And this is non-ideal. What is the equation? Always the same. RT. Same means general equation. What is this? RT x ln A. This is a general XP. Exactly this curve may not be same because the positive deviation this side is the side of A may be different from the side of B. Okay, that is another. So it depends. So actual activity is gamma time mole fraction. Gamma is the activity coefficient. Depends on the activity coefficient. Okay. So that governs actually the max solubility limit also. Here maybe this much solubility maximum. Here this much. Okay. So maybe different. Depends on the activity coefficient. So but anyway, this is the delta Gn idea. So next what to do? The finishing touch. Add this curve and this curve and generate G beta. So no problem. You do this. I can do it very easily. Here like this. Right. So you will not mind. I think this is what. This is I showed G beta. Sorry, G alpha. So G unmixed, don't mix up. G unmixed here. This one G unmixed. This is G alpha. Your desired one. Similarly, this is the desired one. G That's it. This G beta shows here. Shows there. This red curve. This is actually synthesis of this. Okay, this is how they are generated. So this one. Last topic is the figure which is pending. Figure 2C activity versus composition. That is last. So this is, I am removing this. You don't mind, I think, if I remove this. So just quickly just finish this. Next is over. Okay. So this. Next, with regard to figure 2C, the activity versus composition diagram. The activity versus composition diagram. See here written figure 2C activity versus composition diagram. As I told you, what I have plotted I have already explained. ABL and ABS are plotted on the y-axis, two parallel y-axis. And what is ABL? Activity of B with respect to pure liquid B as standard state. ABS is what? Here, activity of B with respect to pure solid B as standard state. This is the caption of figure 2C. And then what is okay? And XB in the x-axis 0 to 1. Then I will consider these critical points A, B, C, D, which is actually projected down into this. So A, B, C, D. This is 0, this is 1, XB is 1. So you have several segments 0 to A to B, B to C, C to D, D to 1. 0 to A, what you have? Alpha phase. See here, 0 to A, which you have? Alpha phase. Then A to B, this is 0 to A to B, liquid plus alpha, say alpha plus liquid. Then B to C, liquid alone. Then here you see liquid phase alone. Then C to D is liquid plus beta. C, liquid plus beta. And then A, B, C, D is where? D is actually removed by this. C, D. A, B, C, D here. D. D. Oh, it was written here, but has been unclear. D. D1. D1, what? Which one? D1, which phase? Beta. D21, which is present in this domain? Beta phase. What is this line? This is a very good reference line. AB is XB. Which one? This one I have shown. AB is XB line. Which one? Connect 0 to 1. This is 0 to 1, 0 to 1. Here, straight connect this point and this corners. So this is AB is XB line. Who will follow AB is XB line? If you ask, see here actually ideal solutions, and liquid solution is ideal. So activity of B with respect to liquid B as standard state will follow this line. Will fall on this line in the segment BC where it is pure liquid. So in the segment BC, see here BC. This diagram refers to, the arrow is shown, AB liquid. This diagram for, see, lower one, repeat, lower one for AB liquid, upper one for arrow this AB solid. Repeat, lower arrow this way means this y axis, AB liquid, and the upper is AB solid. So AB liquid curve will fall on or merge with the AB is XB line. AB is XB line. This one, so easy. Then what you have in the two-phase region, I have taught you the reasoning. There is a horizontal line in the activity composition diagram because they don't change. Activity does not change anymore in the two-phase region because composition does not change. In the two-phase region, as you move, I see the contrast. Liquid you change, move, composition changes. Liquid composition gradually getting higher and higher concentration of A, this direction, or the reverse direction, this way liquid composition is getting more and more enriched with respect to B. But when you enter into two phase, this side or that side, suppose this side, then you don't have any more change in composition. Why? Liquid is tied here. This is called liquidus. Liquidus, this is called solidus in the language of phase diagram. This is liquidus, this is solidus, this is solvus. Similarly, this side, liquidus, solidus, solvus. This is actually eutectic line, eutectic, this one, okay? This one, and hence the name eutectic diagram. So anyway, so what I wanted to tell you here, two phase. Here composition liquid is tied here and alpha tied there. They don't change. So who changes? As I move, relative amounts change. Relative amounts of liquid and alpha. Gradually as you move, here 100% liquid. As you move, liquid percentage decreases and alpha percentage increases, and here it is 100% alpha. This is obtained by a rule called Lever fulcrum lever rule. You will get this. So composition does not change. As long as composition does not change, activity does not change. Another thing you say, what changes here? As I told you, relative amount change. Another name is there. Another way of expressing is this. We call it the gross composition changes. Gross. Mathematical composition changes. Not this. No. The moment you bring this solution here, they quickly split into liquid phase and alpha phase. You can never get a composition of this in between this A and B. No, they'll split. Having liquid of this composition and solid of this composition with their respective amounts governed by the Lever rule, as I told you. So as long as composition does not change, how can activity change? Activity is mole fraction times activity coefficient. So composition depends on composition. So you have a horizontal line. See, so start with this. AB liquid here. Start with this. This is a very good starting point. Start. BC, BC, and this axis. This y-axis is referred to, and XB is of course common. So this to this, AB is XB. AB is XB. Very easy. It merges with the AB's XB line. Very good. You do this. Then you just simply horizontal, because this side two phase, that side two phase. Don't change. Activity does not change. So then you connect this point with what? Zero value at this end. What is the activity of B? Here, because the B is here, B is zero here. Is pure A. But since it is solid phase, solid when activity of B solid is zero, activity of B liquid is zero, because they are related by an equation that I will give you. So zero. So for the time being consider zero, and it should be, because there is no B, it is pure A. So zero. So zero and this point connect. So what you have got? This much done. Up to D you are done. Of this AB liquid, this is the lower one, which refers to AB liquid. Then what you are doing? This to this, how? This is little tricky, and you know all this already, because you know here AB solid is perfectly one, because this is a pure solid B. So AB solid B, other curve, which refers to this axis, is 1. If 1 is known, other is known, because they are related by a relationship. Yeah, AB. So when this is 1, what is the value? I have written here exponential minus delta G0 melting B divided by RT. Perhaps you remember this, okay? Exponential minus delta G0 melting B by RT. Okay, this. When this is known, this is 1, this will be. So this point, so mark this point, mark off here, and then connect. So lower curve over. This advantage you will not get. Okay. But anyway, let me write this. Okay, this much. Otherwise, I will proceed further. About the upper curve, I will explain again. But let us see if writing helps you. Okay. Diagram next. The activity versus composition diagram. The ABS and AB liquid. The ABS, this side, ABS and AB liquid. ABS, any composition choose. ABS value, AB liquid value. They are related by a factor, the same factor. So there is the ratio of these two is constant. I will give you this. Any composition, here, you will see this, okay? So let us see. The ABS and AB liquid are related. AB liquid are related. Already mentioned last class, or say even last but one, okay? That class, okay? 2 classes before. So related, as mentioned previously,
1 hour 49 minutes 30 seconds.
Okay. As mentioned previously, this is
How much more? 10 minutes?
10 minutes. Okay, let us see. As mentioned previously, is what that? AB, note this, AB liquid is e to the power exponential minus delta G0 melting B by RT. Since B we are considering, that's why B. If it is A, then it will be A. RT times AB solid. This is, never forget this, AB solid. Recall, I am writing you recall, okay? Hence here, quickly apply this relation to this point. What is this value? Question. What is this value? See this line, this is 1 is very easy because it is pure solid B with respect to solid B as the standard state. What? Pure solid B, 1. 1 is very easy. What is this? This is not so easy, but will be easy if we remember this. So that means when this is 1, this will be this value. I have written also that. This point, this point E I have given. Point E is this. So this I am writing. Hence this is comment, infer. When hence when AB solid is 1, AB liquid is what? You know yourself that e to the power minus delta G0 melting B by RT. This is actually I am giving as point E. This point, clearly see. E, this value I am giving, exponential, point E. It's very interesting. So this lower curve is perfectly okay. Shall I repeat? Lower curve quickly. This segment, BC, liquid ideal solution, it is considered. So activity of B is mole fraction B, that is AB is XP line. It will lie on the AB's XP line. AB is what? Which AB? The two ABs. AB with respect to liquid, pure liquid B as the standard state. And this is also liquid, so matching, so AB is XP. Then in agreement, the liquid understanding is liquid phase and reference state, standard state is liquid, pure liquid B. So AB liquid. So this scale. So and this diagonal, lower diagonal refers to this scale, remember. Upper diagonal refers to this parallel scale, opposite scale. Remember, repeat, lower to this, upper to this. Don't mix up. XP is common. So clear, quickly, lower one very easy, that's why quickly. So this BC on the AB's XP line. And this I have shown, this you initially, first you draw this 0 to 1 connect. The moment you connect this, AB's XP is so-called Raoult's law line. Just AB's XP. I have written AB's XP. Actually, now actually this AB is AB liquid here. Okay. Anyway, so this you get. Then what? This side 2 phase, that side 2 phase. So horizontal, done. You get here. Which point? B to A you get here. Oh, A is actually is A here. It should be A written here. I forgot to write. I should not. AB, BA down here. Over. The other side is CD, lower curve. I'm sorry, lower curve. CD, C is a C here written here. CD, horizontal. So what remains? Then how will you get this one? Next what you will do? This is AB. Then connect this with 0. Because activity of B will be 0 when it is pure A. For solid, and when you suppose see here, now is easy. AB solid is 0. You say, sir, this is solid phase. Alpha is a solid phase. So AB solid is 0. Activity of A, pure A, is 1 with respect to pure solid A, and your AB with respect to solid B is 0. AB with respect to solid beta, since we are discussing B, is concentrate. AB solid is 0, AB liquid is 0 times this 0. So this is, remember, delta G melting is what? M is what? M is melting. So remember, don't forget. How do you get this? Recall, just if it helps you, recall how I got this. Recall GI bar is GI bar. I'm not writing so many things. R3 activity of the liquid. This relation, you just get back, you get this. Is what? Yeah, this is something important. R3 activity of the liquid is what? GB0 solid minus GB0 liquid plus R3 ln activity of the what? Solid. From this you get this. From this you get this. What is the B solid minus B liquid? Free energy. G0 B. That is called melting. Negative melting. Liquid minus solid is melting. Delta G0 melting. So when B solid minus B liquid is minus delta G0 melting. That's why you have minus delta G0. So you get this. So I am helping you with this recall. Okay. So this figure is complete. Lower one is complete with refer to this axis. The upper one trend similar, but values. So which one will be easier for you? I tell you. See, this side I have actually merged this. Follow. What is this called? D1. D1 is what? With respect to solid, B solid as a standard state. This forget about this side. This over. Lower curve and this over. Solid, AB solid. This is what? This is solid solution. This is, remember one thing I told you, at high concentration a component behaves ideally, follows Raoult's law, tends to follow Raoult's law. You know, when solute follows Henry's law, solvent obeys Raoult's law. Remember those proverbs, those sayings. When solute follows Henry's law, solvent obeys Raoult's law. So solvent at high concentration obeys Raoult's law. So that's why if you consider this side is positive deviation, but when it enters to the very high concentration towards 1, it follows Raoult's law. If it follows Raoult's law, so this segment follow. Again, that's AB's XP line. Line is AB's XP. So solid here, start from this point to this point, this point to this point, this point to this point. This falls on the AB's XP line. Then again, once you have started, you know you enter into two phase. Horizontal line. Then again, suppose stop there. Then again, see here what is this value? Where it is pure B, pure A, so mole fraction of B is 0, so AB is 0. 0 to what value? So this is, since you know AB liquid here, I have to actually, very interesting. You can use this number of ways. This one. Shall I give a bracket? This is so important. What is the significance of this? You know one, you know the other. You know AB liquid, you know AB solid. You know AB solid, you know AB liquid. Using this data, delta G0 melting is always available. Value of R is 8.314 joule per mole per Kelvin. And what is the T? T is the temperature, you know very well. You want your choice, you know. So very good. So since I know this value, Once you know this value, then again then enter into, this is B point, then enter into what? Sorry, which one? I am very sorry. A point. Point A. You know this value. A. You know AB liquid already. How you obtain this? See, follow this. This is this curve. Lower curve is this one. Lower curve this, and this is the upper curve. A, you know. A in the upper curve, you know. Following this. Okay. Once you get this, why I am saying this? Then you have a two-phase region. Horizontal line. So these horizontal lines stop here, and you have stopped there already. You are stranded there. Here you are stranded. You are now here. Connect. This line will be generated. The full diagram is over. For the upper one also, means which is with respect to which is AB solid plotted against XP. AB solid. I should not. AB solid. AB solid means you know the meaning, full meaning. Every day I am giving you. A B solid full meaning is activity of B with respect to pure solid B as a standard state. So please let me complete few lines, just only a few lines. Also note, remove this, remove this. I think I have explained. So what I have said, we will write in few lines. Also note, continue with this. Also note, in view of
2 hours complete.
Acha, in view of okay, thank you. In view of the ideal behavior, what I said I am writing. Wait below 5 minutes.
5 minutes.
Ideal behavior, just in view of the ideal behavior of liquid solution, AB liquid is XB, AB liquid is XB, is exhibited by the single phase liquid solution, by the single phase, not two phase, single phase, this one, B to C, by the single phase liquid solution, by the single, who is this, what is the range, by the single phase liquid solution in its stable domain, in stable range B to C, in the stable range B to C. So it will follow a bit that I said. Okay, then next is what? B to C is over. In the domain D to 1, likewise in the domain D to 1, as I said, D to 1, approximately Raoult's law of solvent tends to be able, ideally AB solid, and it is following AB is XB, means goes to 1. Okay, AB is XB, falls on the AB is XB line. In the domain, in stable domain, in the domain, quickly. In the domain D to 1, AB solid now. AB solid is shown to lie on, AB is XP, again AB is XP line, because it becomes Raoult's law. AB at high concentration is AB is XP line, is shown to lie on AB's XP. Where I have shown, shown here. This is the AB's XP line. So it has fallen on the AB's XP line. So AB, as I have already said. So this may be considered. Maybe why? Because almost ideal, or Raoult's law tends to follow Raoult's law. So may be considered valid because at high concentration of I, I say any phase, A or B, so I call it I, concentration of I, that is X side tends to 1. X side tends to 1, component I tends to follow Raoult's law. What is that? AI is X side. That I consider, at high concentration I consider. If you don't consider, then you have to give a positive deviation here. So activity is greater than X side, and finally it will be 1. So like this I can show. I've shown this way. You may show this is 1. This is show this way. Marginally at the 1. Okay. This is a deviation from AI is exact. That may be possible. Okay. But for simplicity, I have shown this. Thank you very much. Hello. Thank you very much for your, okay, today's topic is over. We'll take up the third topic on this free energy versus composition and activity versus composition diagram. Next, for the binary system, maybe third one, that is eutectic system with a chemical compound, intermediate chemical compound formation. Thank you very much for your cooperation and for your interest. Thank you. See you next class. Bye.